So I think we can move on with part 2, compilers, the why and the what. One of the consequences of our design of using a proof on-chain is that we need developers to make proofs, which means they need to make circuits. Their programs have to make proofs. And there's 2 real ways to approach this. The first is to just teach them how to do it. And this really sucks because it's like a lot of work. It takes a few months to learn the cryptography and start building the circuits and learning how to debug them. And that's just a big barrier to entry and slows down production times and all this kind of stuff. It's really not ideal. So the other solution 2, is to make code, make circuits by itself. If you can write code in a language that's similar to one and you don't have to deal with the circuit directly, we can automate away some of this process and make it a lot easier. We can reduce the knowledge requirements in terms of cryptography and also bring down development times, which are both really important. And this is why we made Leo, and it's why Circum 2 exists, and Noir and Cairo and all the others. It's to make the life of the developer easier and help us achieve value more quickly. We talk about compiling to circuits, and this just means you're writing your code and turning it into a circuit. I just want to go over the whole kind of process here. You have your high-level idea. In this example, it's a voting system. Voters do this to vote, and vote tallying occurs by this other thing. We're going to want to add some more detail where we're going to say votes are curve points on a BLS curve. Maybe encryption is through this thing and decryption is through this other thing. Then we have to make our circuit. And what I have for you here on the right is these are constraints in a rank 1 constraint system, which is a type of snark. So these are the things you're actually using in your program. And we're going to have to discuss a little bit how you turn a voting system into things like this. And then you do your computation and you get out the proof. I'm going to be discussing these constraints with you to some extent, and I may be throwing you in the deep end a little bit, but part of my point is going to be that you don't want to work with these constraints directly. I want to because I like it and I find it fun, but most people, it's not relevant. If you're trying to build a product which you think is going to help people derive value in the real world, you want this to be as automated as possible so you can focus on the parts that you know and understand. But I'm going to explore the constraints just to show you a little bit of what's going on. On CS values, in these constraints, this x1, this x2, this e, this v, they are they U8s or are they characters or what are they? They're all specific things. They're all just numbers, specifically numbers between 0 and p minus 1. Now, the size of this p is determined by the elliptic curve you work with. But they're all field elements. They're all just numbers between here. So you don't have a U8, you don't have a character, you don't have a string. And we're going to have to learn how to use these field elements along with constraints to have all the functionality that we want. So this is, very abstract. In a computer, you have all these NAND gates, and if you put them in the right ways together, you can do logic and you can run a CPU and you can do graphics processing and all this other stuff. But in a proof system, this is the starting point. And for reference, this size of P, it's massive. This is BLS 12377, which is the curve we use at Aleo. And this number has, I think around 10 to the 80 digits after it. And that's a phenomenally large number. It's like the number of particles in the universe. And I mean, our solar system is only a tiny part of those number of particles. And I feel like there's a lot of stuff happening here. So you can do a lot with the numbers in between this space. Yeah, and it also gives us some of the security properties. As for the constraints, so these bullet points, these are just examples of what it can look like. x2 equals x1 multiplied by x1. Second example, a third example, but they all have to satisfy this bottom equation. And I know this can look a little scary, but you don't need to worry about the details. It's more useful to understand a few of the examples and see some of the properties. For example, I don't have any squares anywhere. In the first constraint, I have x1 multiplied by x1, which is x1 squared, but we don't want to use any higher power in the constraint system. So we just call it x2. In reality, it is x1 squared, but we won't do that. We'll just call it x2. Yeah. Okay, so binary operations. We have one of these x values, let's have it x. What if we want it to be a binary operation? What if we want to ensure x is Boolean, that it's 0 or 1? Now, I have a question for you here. I can give you 1 or 2 minutes, and I want you to see if you can figure out what the constraint should be. What I mean by that is, can you come up with an equation like the first line, where it will only be satisfiable if the x in the equation is 0 or 1? So I'll give you 1 or 2 minutes to see if you can work that out and play around with the math at the heart of this. So as a hint, what property do only 0 and 1 have in common among whole numbers? I'll just give you a minute here to see if you can write something down, and then I'll go through what we would expect. Okay, so hopefully some of you may have worked out that we would expect something like this first line. We have x multiplied by x minus 1 equals 0. So, well, the right-hand side is 0, so that means the left-hand side must be 0. And if we're multiplying two things together, then to get 0, one of them has to be 0 itself. So either x is 0, looks good, that's what we want, or x minus 1 is 0. And if x minus 1 is 0, then x must be 1. So the only x that satisfies this is x equals 0 or 1, which is exactly what we wanted. Also below, I have the same representation. If you expand the bracket, you get x squared minus x equals 0. But this is something that you kind of want to avoid because we have this square here, and I mentioned that that's something we shouldn't really be seeing in a constraint system, even if it is happening implicitly. I want to give you one more of these problems to see if you can solve. This one's a bit more involved and harder. We have an if statement. So if x equals 1, then y equals z. Else if x equals 0, then y equals r. Okay, this is more of a selector where you have 0 and 1, but I couldn't get the maths to render, so I just turned it into an if, else if. And I'm wondering if you can figure out what this constraint should be. And I'll give you a couple of minutes here again. So again, this should be an equation, something like this, probably involving, well, we have an x, we have a y, a z, and an r. And it looks like we're saying, well, y should equal this, or y should equal that. So maybe the constraint would be y equals something. And I'll just give you a minute here to see if you can work it out. And again, one of my points about doing this is that for a lot of people, they don't really want to work with these constraints or this maths or have to understand what's going on. Ideally, we want it to be done for us so that we can focus on the other parts that we care about more. Okay, hopefully that was enough time to play around and see how these things work. You may have ended up with something like this. Just quickly, the lower line, this is the constraint that we had before, because if we see x has to be 1 or 0, it just makes sense to do a binary check. And then we have y equals r plus x multiplied by z minus r. And let's check if this does what we want. So if x equals 0, then y should equal r. Well, if x is 0, we have y equals r plus 0 multiplied by something. Well, that's going to be 0. So we just have y equals r. And okay, that's exactly what we wanted. First part, good. What about if x equals 1? Then we have y equals r plus 1 multiplied by z minus r. So r plus z minus r minus r is 0, just left with z, y equals z. Oh, okay, this is what we wanted. Cool, we got it. So we have libraries that will make these constraints for you. You would just put in a selector and it would do this part for you, but you still have to kind of understand with the library that you're using what this gate is doing and some of the quirks there. But our compiler is going to be automating a lot more for us. Okay, so that was previously we did, Booleans, but what about a U8? How do you represent a U8 in an R1CS? It turns out that for design reasons, it usually makes sense to separate, not just have one thing that represents the U8, but have a binary decomposition. So you'll have 8 variables, and each of those 8 variables requires a binary constraint. So that's already 8 constraints. Then if you want to use the U8, you'll have to sum them together in the correct way. That's another constraint. You add up a lot of these constraints, and it gets a bit confusing. But this is to work with some structure that we're used to, a U8. And compilers are trying to do as much of this as possible for us. Now, how about if you use the library to build a circuit, you try to turn your program, Hangman, into code, into a circuit. What if the proof fails? What do? If you look through the code and you say, well, this does what I wanted it to do, then the problem isn't your code, it's you need cryptography to debug it. There's some quirk about a proof system that you currently don't understand that's preventing you from making your circuit work. So if you want to be able to debug that, you're going to need some cryptography. And as we said, this is a very high barrier to entry. You're going to have to spend a few months learning the cryptography and playing around with things and trying to get them to work. And yeah, we're just going to have fewer developers if that's the case, and slow down production times. Now, I just wanted to touch on one thing that Tesla has apparently done very well. They don't just try to make good cars, they're also trying to make factories very quickly. They broke ground and had a functioning factory making cars in Shanghai within a year. Looks like similar time for Berlin in Germany. It looks like a similar time in Texas. If you're another car company and it takes you 4 or 5 years to make a factory to output the cars, and your competitor can do it in 1 year, you're not going to be in as good a position as them, are you? Also, it's just going to take you longer to derive value from the thing you're trying to make. And if it turns out there was something wrong with the thing you're trying to make, then you've wasted a ton of time building it to learn that. So we want to make this process as quick as possible. So we have Leo, and we try to add in as many properties that's going to be useful for this endeavor as possible. It's similar to JavaScript and Rust. Many people in the blockchain space use Rust, so hopefully it should be quite easy to learn. Moreover, there are 12 million JavaScript developers. It's a huge, huge pool. It makes sense that we should try and get some of them to join our space to build things as well, particularly because our applications need a variety of builders. And I think in general, blockchain has a big UX problem, user experience, how you do things. I mean, I'm still terrified every time I send crypto to do anything, and anything else I do on a blockchain, I do it more because I think I should do it, as opposed to the process being easy and nice. So we've got some way to go there. Leo also creates the L1CS for you. Just kind of been over this. There's a testing framework, so you can do unit tests and ensure your application runs as you want it to. We've got a package registry so that you can quite easily import other code that people have made and reuse their things to save yourself time and borrow kind of the expertise of other teams. We've got an import resolver, and this will be formally verified by ACL2 theorem prover, and that is that the compilation was done correctly. And again, these are all the things that we're putting into Leo. That's not to say that it's quite yet done, but we're almost there. One thing I want to focus on a little bit is implementation bugs. There's been a lot of losses because things have not been implemented correctly, in the cryptography or other parts. Now, if you need to build something, and very simplistically, let's just say you have to do 10 things, then there's kind of 10 possible places you can make mistakes. But what if lots of people have to do some of these things? And we say, well, these 6 things everybody has to do. So why don't we get some smart people together to build some stuff that automates and does those 6 things for us? Then you have 4 things you need to do, 4 places you can make mistakes, and the other 6 things are done by some automation software that some very smart technical professionals created to try and reduce the possibility of something going wrong. So compilers are trying to help a little bit as well to prevent some of these attack vectors. What can you do in Leo? We have all the data types you're probably used to: U8, U128, I8 to I128, also fields, elements, characters. We've got emojis, it's quite fun. We've got structs with implementations. If you know Rust, you can define a struct with some things in it, and then you can define some implementations on it. And this is what we have. We've got if conditions, we've got for loops, and we have bounded recursion. This is one of the quirks of proof systems. You can't have unbounded recursion. If you're creating a circuit, you need to know how many recursive steps you have. And if the number of recursive steps depends on your input, you have a problem. But what we can do is bounded recursion. We can just say, hey, let's just do 20 recursive steps. If you only need 10 of them, then you'll do your 10 recursive steps, and you'll just do 10 dummy recursive steps, and you'll be able to make a proof of this. But you won't be able to do more than 20 recursive steps in this design. And this is one of the quirks that you'll have to just understand that it exists, not necessarily why it exists. What are the knowledge requirements for using Leo? Well, again, one of the main points is that we want it to be minimal. We want it to be as easy to use Leo as possible. So the cryptography happens under the hood. It's all done for you. The proof circuit and proof will be made for you, and you won't have to touch any of it. It's kind of just like a translator. Now, if I was to ask you how Wi-Fi worked, what would you say in response to this? Your phone sends signals to the router, but like, what wavelength is it sending? What part of your phone is sending it? What are the protocols for processing the data and sending it off? What's happening in the router? I don't know any of those answers, but I can still use Wi-Fi. I can still build things of value that use Wi-Fi. I don't need to know any of those things. So my point to you is that you don't need to know how a snark works. You don't need to know how a compiler works. You just need to know what they do to have a functional understanding. The compiler is going to make a proof for you. Proofs are smaller, which means your blockchain can do things more quickly, more cheaply, and maintain some privacy for you. And now you can code in Leo, write some program, and use it. You don't need to know the details. It doesn't make sense. If everybody had to learn the details, it would take us a very long time to start building things that we want to see. Okay, so the things you do need to know, you're going to need to know our transaction model, which I'm going to touch on just a sec. And then you want to know like program and functional capabilities. I touched on the bounded recursion earlier, which is one quirk, and there's a couple other quirks going on there. But mostly, generally speaking, should be quite similar to languages that you're used to. As for the transaction model, we're currently kind of upgrading it. We're trying to find the global maximum in how good it can be. And there's things here called transitions and transactions. So a transition is up to 2 records in, up to 2 records out. And this is the base thing that actually goes on chain. But possibly you have an application where you need more than 2 records in or 2 records out. In this case, you can string transitions together to make a big transaction. And here is a directed acyclic graph to represent that. So for example, number 1 here, this is a transition, takes in records A and B and outputs record D. And similar thing going on all the way here. And all records D to J and all transitions are going to be sent to the chain. You know, just because D, E, F, and G come into existence and vanish essentially immediately, doesn't mean they don't go on chain. They still do go there. You may be wondering why we have 2 records in, 2 records out. Why not just more of them? And this again is kind of a quirk of proof systems. If we said that a transition could take in up to 10 records and output up to 10 records, well, the transition is actually a Groth16 proof of verification. So your transition always has to take in 10 records. If you only needed 2 of them, you still have 8 more records. They're just dummy records. But your proof is not as small as it could be. And this is why we want to make it small, but provide the option of stringing them together to add more functionality. But again, we're still in search for the global maximum in terms of how efficient this can be. We also built Aleo Studio. This is an IDE. You can download it out Aleo Studio. And again, it's just to make things as simple for you as possible. You can also use it in VS Code. And syntax highlighting will be available soon and makes developing a lot easier. Cool. I hope you enjoyed part 2 and understanding and provide some context as to what compilers are for and what they're doing, and give you some references to when you should be using them.